Well, hello everyone. Welcome to instructional course number 56. My name is Dave Brienza, and it's my pleasure to introduce Bart Heyden and Alex Siefert, who will be presenting, actually, they'll be introducing digital validation of design and seating interventions. Before they get started, I just want to let you know that we'll answer questions at the end of the hour. We'll take about 10 minutes at the end to have discussion and questions. But feel free to enter them as you go. As the speakers are talking and a question comes to mind, put it in the chat, and I will compile those and try to organize those at the end for the speakers. And the other thing I wanted to tell you is that the CEU code will be provided at the conclusion of the session. So with that, I will turn it over to you guys.
Thank you, David.
Thank you, Dave. Bart, it's you. You can start.
Can you go to the first slide, please?
Yes, sure.
Yeah, all right. Thank you all for attending. Very exciting to have you here. My name is Bart van der Heyden. Very close, Dave. Thank you for the introduction. It's a Dutch name, but I live in Belgium. I'm a physical therapist near Ghent, a very beautiful city, probably the most beautiful city in Belgium, at least. I'm a physical therapist. I specialize in seating, wound care, and mobility for over 25 years. Worked in Germany, US, and now I'm back in Belgium. I have my own clinic. We have a small team of physios. We have 5 physios in our practice. And I'm also doing training, seating courses, consultations of clients with complex seating worldwide. And I do this on the name of super seating, which is basically me. So that's also my disclosure and conflict of interest. I'm very excited to be presenting together with Alexander, and I have been presenting for several times now. We're trying to link the clinical relevance of finite element analysis, and we trying to look at what the interesting topics are for the clinical community. So we're looking at impact of different seating interventions today, tissue stability, tissue deformation, and what the impact is for the client when you change the back support angle, pelvic support angle, and we're also going to talk about seat angle variations. So Alexander calls this design of interventions. Over to you, Alex.
Thank you, Bart. So I will also introduce myself. My name is Alexander Siefert. I'm located not in Belgium, not in the Netherlands. I'm a pure German guy located in Bavaria. I'm managing director of Symposium. Symposium is a company. We are providing software, but also doing consultants. I have about 20 years of finite element expertise, especially in the field of seating comfort analysis. I was working a long time for car seats, but been in this business of wheelchair users about 10 years, I would say. I'm the developer of the virtual human show, which we will see in some slides. And here you have my contact details and also my information about disclosure. So let's start directly with the first part of that. Before we go to the cases which have been described by Bart already, the 3 setups, we will give you a little bit an introduction of finite element analysis. Maybe if you have joined us some years ago at our last presentation, ISS, so this is just showing an overview about that. And some of them is, just showing what is the benefit of using finite element analysis. So finite element analysis itself, it's a standard calculation tool in many industries, and it can be used for simple setups, but also very complex setups. So what we see here in this setup, it's used there for a frontal car crash. And this video describes very, very good, in my point of view, what is the benefit. So the first part, which we'll start now, this is a real car crash. The second part is already virtual, what means it's only computed in the computer. And here you can see, using that method, we have the possibility at all stages of that simulation, we can look how does the structure behave. Where is the strength and where's the weakness of the structure? How can we optimize that? So what we, based on that, we just define that the benefits, no hardware is used. For the car crash, it's very clear, but you will see also in some slides, there's also benefit in the setup. We're discussing that here. 100% reproducibility, what means there is no influence of test persons, of setups. We have a know-how increase. We can look inside to that. And we have obviously a time and cost reduction. So, and you would ask, okay, it's automotive seating, but is this already a part of our industry? Is it more in the medical industry? Yes, it is. I have two examples here. This on the left side is a gait footwear analysis. You can see really it's augmented reality. So in the background, we see really the movement of a person. And then you see really what's going on inside, inside the leg and what's going on, especially for the design of the footwear, where are the pressure peaks? So this is an interesting task, a different industry, but you can see directly, okay, it's used for medical devices. And here another setup, maybe you heard of that. Many people need replacements of knees. And here this on the one side, you see the animation of a real test. And on the right side, then in the small part here, you see this is a simulation. And you can also have a more detailed look, looking on meniscus, looking on the ligaments. And this is the benefit. We can look inside to that. Why we think maybe this could be helpful in this industry, because we think so far there's a lot of expertise. And this is not here just to replace the expertise you all have working a long time with the patients, with the customers. No, it's just giving some additional information, getting some more setups, especially evaluating products or designs. So here we see typically we use indenters to compare setups to each other, to make certificates. That's okay. But the question, if you want to do an optimization of that structure and you do a test person test, this is not really 100% reproducible. It's not really, when you look on indented, it's not a real scenario, but then in this case, it's reproducible. Are we looking on the right evaluation quantities? Rigid indenter, maybe, then we see a force deflection value, but is this really giving us more information about the tissue? Digital, yes, we will see in next slide, we can do this digitally, but it's not, I would say, state of the art. And time or costs, if you're very fast, like some laboratories to produce new hardware, you can do that very fast and with reduced cost, but it's not so easy. Giving a more detailed information about using that method in the work we are talking about here. So I just did Sunday morning, 10 o'clock up to 12 o'clock, I did this small tests. I settled up a foam cube, very simple, you see that, and just to place the ISO indenter on top of it and do a typical analysis, just putting 800 Newton there, and then see how the indenter is settling down and have typical values like we see here in the middle part. We have the pressure distribution, nothing new for you. And I also can plot here the force deflection curve, nothing new to you. What is the difference? I can also look here on the right side on the friction, what means how the indenter is moving with the cushion itself, the friction. We know there are some indenters out there for standardized. They can do some friction values, but they have not the resolution for the whole surface. They have only one specific parts. And especially if you're interested what's going on the IT region, when we later come to the human body, then you need a higher resolution, the first benefit. And a second one I can easily describe also by this example. I did two setups. The first one, it's really a continuous foam block, like we see it here on the left side. And then on the right side, you can already see there's some higher or some lines with a higher intensity. And I just said, okay, I make cuts to that foam. Also did it in 2 hours. And then I did the same test as before, just putting gravity with 800 Newton. Then you see that the SI indenter is going down. And then I said, okay, let's see what's going on if we move forward. And there you can directly see the difference. And this is a cross section at the sagittal plane. On the left side, we have more continuous setup. But what is interesting, we know there are some products out there have cutting foams. And we know there is a difference, but maybe we have not all the information. What does it mean? Which is the size I should make my cuttings inside the foam or other setups. And you directly can see here, I can look on the interaction in the cushion at the foam splitted setups. So this is just a simple model, but visualizing the possibilities we have. So this is now giving a general introduction, now giving more details. Okay, we want to talk about seating interventions. Seating interventions, just looking on a rigid test indenter is not enough. We have to take into account the human body. And what you see here, this is just the animation, but also calculation. It's just a rendered style as we had it before, just where you can see that Joe is placed on a wheelchair and then he's thinking on that. So Joe is based on a skeleton data, CT scans data, and the layers of the compliant tissue, what is adipose tissue, muscle tissue, is based on MRIs. And we have some additional validation setups. We worked a lot on the lumbar spine modeling, what means nucleus, annulus. We worked a lot on other parts, ligaments, muscles, and we just make sure that Joe is representing as good as possible a healthy person. You would say, okay, now he's using a healthy person. This is not really showing us our patient. But the question is here, if I have a healthy person and I see a tendency between some designs, then I will see almost the same tendency for a real patient, maybe not in the same level, but I can say this product shows a better behavior than the other one. And then also this part, a first part with the healthy person is a good setup. And it's only a starting part because the problem is to have a patient-specific model. You need data from the patients. It's not only geometry, it's not only the bones. You need especially specific data for the tissue. And this is difficult to measure, but hopefully in the future we get more information with that and then have patient-specific models. So why we are using that setup? Because we know from some very known setups of Kees Omens, you all know him, that they have made a lot of investigations where they found, okay, the direct deformation of the tissue is really a critical part that you have necrosis. And we have typically four setups, but only we look mainly here on 3 setups. We have pressure, so you can see here, we can simulate pressure at the surface. Second point is friction between the surface of the patient or customer and our seat surface. And we can also compute shear or any kind of internal tissue stress, because as I showed for the cutted foam, I can also do that for Joe, look inside in his tissue and get there an idea what's going on inside the tissue, giving us more information about the setup of loads, how the loads are transferred from the skeleton finally to the seat. And then the question is, okay, you can see, for example, when I look on the right side on this colorful picture, and now imagine I have 5 design, I make always the cross section. Then I have to find out, okay, is it always the right cross section? Will I only focus on the hotspots? Did I get all information? How can I summarize all the information in one plot? Because if I have 5 designs, how difficult it is with these colorful pictures to make a decision? And then a long time ago, together with Bart, we worked on a procedure. It's already known from some other publication. We call it the volumetric strain distribution. And what we are doing here is a little bit shown on the slide and on these animations. And what we are doing here on the left side, you see a settling down, you see the pelvis, and you see the wheelchair. And then step by step, after the gravity, if he sinks down to a gravity load, more and more tissue has a higher level of strains. And we can find out or compute which part of the tissue is in a specific strain level. So we can say at the end, you will see that on the right again, after putting more gravity load, you get more and more tissue, because here is only the tissue is shown above 40% of compression. We see more and more tissues in that range. And then we, at the end, when he has settled down, we can say, for this setup, this amount of the tissue is between a low value up to 10% of strain, 20, 30, 40, 50, 60, 70. What does mean strain? Because you already hear by my words, I'm an engineer. And sometimes, yeah, it's difficult using my words for your setup. And you see Bart is smiling because he said, make sure these are not engineers in the audience. Maybe some, but not all of them.
Yeah.
Not all of them. And so what is strain? So if I have a beginning setup and I have a compression, then strain is a quantification how much change of volume I have in that. And more strain I have means that I have more compression, and more compression, we know the deformation is somehow defining the risk of dying of cells. More compression or more shear strain means higher risk of dying of cells. And this is what we want to prevent with our seating interventions, with our seat designs. So the question is also here, colorful pictures, 5 designs, 5 setups, no idea how to do that. And I mentioned at the end, we can separate how much tissue volume has a higher compression, so a higher risk, and we can separate that in different setups. And the reason why we separate it in different setups, it's known there's some threshold values. It's normally between 50 and 80%, where, you know, if you're in this area, you have a risk that cell starts to die. If it's above 80%, then you have directly, you're sure that it dies. And this is also known by some tests coming from the TU in Eindhoven from Kees Ullman's group. So, and still colorful pictures, but we transferred that. At the end, we say, okay, we can compute really the tissue volume, which is shown here on the left side. And we show how much of the volume, and we concentrated really on the area of the ITs, how much volume is between 0 and 10%, so no risk. Below 10%, below 20, below 30, no risk. Below 40, 50, it's getting interesting. If we have values above that, then we know, okay, this is getting critical for pressure injuries. So, and now you can assume if I do this bar plot for different designs, I can easily compare them to each other and say, okay, if I have a higher bar plot value in the risky area, then this design is worse than the previous one. And this is what we want to use finally for evaluation, not only looking on pressure maps, on surface plots. We are just doing the simplified analysis using VSD to compare easily, and you will see that later on. It's really easy to understand that, how we can transfer the information and make it simple to understand, and maybe also to share with customers or patients that they get an idea what's going on there. So, and I will now hand over to Bart, introducing more of the clinical part of our pilot study.
Yeah, because I see people already thinking, where does all this information fit into our clinical decision-making model? So it depends, you know. So if you have an intuitive clinical decision-making model where, oh, the client is sliding, the client has a poor head position, I need a solution, I need a new back support, I need a new head support, and you're kind of done unless the client calls again. We call that an intuitive clinical decision-making model, where there's not a lot of reflection, not a lot of knowledge, not a lot of assessment on the individual needs of the client. Then I think it won't work, you know. So, but if you go to a more analytical clinical decision-making model, on the next slide, please. Whereas you look, can you go to the next slide, Alex? Thank you, sir. Where you're looking at the client's individual needs, and then you figure out, for instance, if the client is sliding, what do I need to know about sliding? What is causing it? And also, what are the consequences of sliding? And we will discuss this with the seat to back support angles and the seat angles itself. Then you have a more informed decision for a client, but you still need to investigate the individual needs and the individual possibilities. And that's what we call a seating assessment. And that's the information from the user, which is always specific. And you still need to apply that information to a client-specific situation. And then you set your goals, you do your seating interventions, and then you track your outcomes to see if your clinical decision-making has worked and if you have outcomes that you were expecting to have. So that's kind of the approach that we would prefer. And I think finite element is not replacing the need for hands-on assessments, unfortunately, or fortunately for us, I would say, but it can help you with a client-specific decision-making if you're applying that knowledge to the client situation. So your seating assessment will still be very important. All right, over to the next slide. Very exciting, the moment we've been waiting for so long. What happens if you change the seat to back support angles from 95 to 115 and then back from 115 to 95? Now, we all know that this is happening all the time. I looked a little bit on what is out there in terms of guidance for us in order to predict what the effect will be for our clients. There is a resonant position paper on the application of wheelchairs, seating systems, and secondary supports. And I abstracted there a couple of interesting quotes or findings. They refer to a study where ALS clients used recline most frequently, more so than tilt and space functions of wheelchairs and more than elevating leg supports. So that was, so it's just an indication on how frequently recline functions, back support recline functions are used. 28% of that sampled population uses back support recline functions between 11 and 20 times a day. So we need to know what happens, not just going backwards, but also going forwards or closing the back support angle. We also know that clients have sometimes difficulties with these functions. I give you the typical example of a tilt in space wheelchair with a back support recline function, and you are intended to tilt the wheelchair in space, but by accident you reclined, you go into a full recline, back support recline, and then as a reflex, you put the climb back into a more vertical back support angle, and you hope that you didn't do anything wrong. So we're going to see hopefully we're going to see what's going on when this situation is occurring. And also the resonant positioning paper reported that some clients dislike their head supports when the recline function is used. And that's probably to do with the axis of movement of the back support recline. If your back support recline is moving at a different axis of movement as the client, that probably will introduce shear and friction forces at the back support. And we also know that, of course, changing the back support will change the sagittal tie to trunk angle of the client. So it has an impact on hip mobility. You need to have hip mobility to do it. And further on, we see that recline is believed to, or is thought to reduce shear forces, increases shear forces, but reduces pressures at the ITs if you recline above 90 to 100 degrees. And that's kind of roughly what we have to deal with. So if you go to the next slide, I'll give you a perfect case illustration of all these problems come together. This is a client with cerebral palsy, has a subluxation of the hips and a reduced hip flexion possibility. So we have an issue here. We cannot sit the person upright without having a hip extension. So we need to increase the tie to trunk angle of the client, so that in the middle picture you see the client seated on the edge of the table of his bed. And then when he's sitting in his wheelchair, he sits with an open tie to trunk angle, and we don't really know what the impact will be on tissue, friction, and stability of the client. Help, Alex, can you help us?
I try my best. So what we do in the analysis, we made a simple setup. Just foams, a cube foam on the cushion side and a back foam with typical hardness value. And we said, okay, we will do 3 simulation steps first. And you see that now loading by gravity. So he's settling down. On the left side, you see the deformation. On the right side, you see already some information, what's going on in the tissue, sagittal cross-section, showing the strain energy, which is an indicator of deformation. And then we just moved him backwards about 20 degrees from 95 to 115 degrees. And then we moved him once again forward. And what I have to highlight here, this is not that we positioned him, it's a dynamic seating behavior. So it's really real-time simulation. And we used in this case about 4 seconds moving him backwards and 4 seconds moving him to the frontal side. And the question was, okay, let's have some looks on the evaluation criteria we have been presenting before. The first one on the left side, and you see here the scale is millimeters of mercury, is the pressure map. And this is somehow showing what Bart describes. If we start with a recline, so first settling down, if we start with a recline, when we focus now on the ITs region, we see step by step, now we do the recline, step by step, we see a reduction, we see some increase below the sacrum. And if he comes back, he's getting to a similar setup as before. The second one, I said already, we cannot really measure, but we can compute that, do an analysis on that, is the fracture map. So settling down, I used here also the value of millimeters of mercury. We see we have already below the ITs, a little bit in front of them, we have some shear. And then starting when he's sliding backwards, we see especially sacrum, we see more shear. And then when he's moving, it's really reducing. So this is somehow expected what Bart describes. The problem, what I see here on the left side, yes, I can do some evaluation. On the right side regarding the friction, it's a little bit difficult. And therefore we decided here to go on in VSD. And the next animation is similar as before, but directly showing that. Left side compressive strain, above 50% critical area. So you can already see to settling down, this is now starting after gravity is applied, and the right side is showing shear strain, more critical than compressive strain. And we see what's happening. Now he starts now to recline. And then you can see, especially on the right side, that the shear strain, it seems that you get more finite elements, what means more tissue volume, which is in that critical range. The compressive strains also changes, but we not really can do a detailed evaluation. This is what I said. When we only use these colorful pictures, we get some idea, but we not really easy can compare designs to each other. And therefore, we converted this information to some bar plots. And this is a very good example. So now here we show you only the critical values. We say, okay, it's starting with a light green at 5 degrees, what means 95 degrees of the back support. And then we go up to 25 degrees backwards. And we directly see for all setups, for the lower percentage of the strain, but also for the higher, we see what we have really seen in the pressure mat, and we can evaluate that. We see really there's an unloading, a reduction of the compressive load. And when he comes back, we are getting to a similar value. So there's no change, but we can prove by that it's an unloading. And this, in my opinion, is also a good example where you can explain the patient, okay, this is really going on, instead only of using maybe backrests, pressure maps. But more interesting is for us when we look on the shear strain, because we have no measurement values. So, and here we will focus a little bit on the higher strain values, especially on the 60 to 70% setups. Same colors, light green is the starting point, 95 degrees, going up to 150 degrees, and then coming back. And here we directly see for the critical area of the shear strain, we see an increase. This is what Bart describes. But what is more interesting is when you come back, and he's not coming back by his muscle force, he's somehow pushed back by the backrest support. And you can later see that on one of the next slides. He's really pushed back. This means they're sliding and he's pushed inside the seat cushion. And based on that pushing forward, we see not only that there's an unloading, we see directly the inclining, reducing the seat back support angle is really making a different level. We are on a higher level. We can also see at the final, we are at higher levels than the starting point. What means you cannot say, yes, I get only an increase. When you come back, you're at a higher level of shear strain. You're not reaching the same state part. And this is maybe also an interesting point we get from this dynamic analysis. But the question then we raised in the discussions, I said, okay, what do we think will happen if we repeat that? Because we know, Bart told me, okay, and we have seen that on one of the previous setups, they're not only doing it once, twice, 3 times, 5 times, several times over the day. And the question is, will it change? Will it come always back to this solution? No, it will not. So we did the same. We just repeated twice, increasing the angle up to 150 degrees and going back to 95. You see that now? And you already, when you're here, look on the right side, you already, when he's now coming back and look on the frontal part of the thighs, you really visualize that. And this is also something where I think, okay, this can be an educational video for users to understand, okay, I'm really, maybe I have not the sense for that, but I can see that. And if you now convert that once again to the mechanical quantities where we can do some risk evaluation on top of that, we come to the pressure map once again, and also the friction map. I will start both of them. Slight difference, you can see that, but the difference are so small that on these colorful pictures, it's difficult to make really a setup. And therefore we decided also go for a VSD plot. This is making it much clearer, and because you directly see the tendency we have there. And once again, I would emphasize the tendency will be there if the client is not a 50th percentile of male as we have it here. It will be somehow, because it's a typical mechanical behavior of changing this angle. And what we see here, this is once again the compressive strain. And we just have, I just use the same colors twice, starting here, and I will focus here on the higher percentage starting here. You see an unloading, and you see a second unloading, similar slight change. I would say regarding compressive setup, it's not really changing a lot. Yeah, we see only what we described before. We see an unloading of the tissue in the critical areas, benefit of using recline. But then we looked also on the shear strain. And I will also focus here on the higher percentage. This is the first part we have seen before. What means if we do the recline, so increasing the angle, we see an increase. And then if he's moving back, he's somehow pushed in the seat. Yeah. And then we can see on the second loop, he's already having for the second part, he somehow keeps that higher level. And especially if we do a second reduction of the angle, we also get an increase. And this is what I said, we can visualize that by the small movement of the thighs, but directly we can say, if I will repeat that increase and decrease of the seat back support angle, this will be I will not reach the same state. It will increase, increase. And when I show that to him and I can tell him, okay, this is very risky for your tissue, then I directly can describe him, okay, let's do a repositioning. Directly do a repositioning, because if you do a repositioning, then you come back to the initial state and you prevent that the level of the shear strain with the risk for pressure injuries is increasing and is decreasing. So this was our answer to that. And now I think we are coming to the second case.
Yeah, very interesting. It also explains why we need to reposition our clients after using the back support recline function several times. So very, very interesting. The second setup we wanted to look at was changing the sagittal seat angles. And we're going to change them from 0 to +5 and to -5. And we're also going to look at an ergo seat, which is basically a shape that is sometimes built into ergonomic or active wheelchairs. And the tubing and the shape of the canvas is designed to provide a pre-ischial support and a lower part to support the ischial region. So we're going to look into that. There's not so much evidence out there on the influence of sagittal seat angles on tissue. So we know that it influences the client's thigh to pelvic angle. So it will also require hip mobility. So that's important for your seating assessment. We also believe that it has a lot of significant impact on posture. It probably helps to prevent sliding. It can also help to stabilize a client. It can help, if you're stable, you can probably use your upper extremities a lot. It's a common strategy to increase the sagittal seat angle for clients with a tetraparetic condition, because it's increasing their stability level and it helps them with propulsion. But we also know that it comes with a price. The transferability might be compromised because you're sitting higher up front at your distal thighs, and leaning forwards might also be more affected, or you will have less possibilities to do so. But we believe, or we think, it can impact sliding. So a case illustration. We have a client also on the left, and the client on the left is a client with cerebral palsy, has a range of motion deficit, and she prefers to have a negative sagittal seat angle because it helps her then to sit with the trunk upright. So that's the choice we're making here. And it works well for her. And on the right, you see another client with cerebral palsy. This client doesn't have a hip subluxation, but she prefers to sit with a positive seat to back angle. And the reasoning why is when you are closing the hip angle, it has an impact on extension thrust and tone. So we know that it works for a functional condition for these clients, but what is the consequence on tissue deformation, friction, and shear? Alex, can you help us?
Yes, I'm here for your help. So what we
Yes.
did, we just used the same setup as before, and we make simple variations, just covering that sagittal seat angle. And you see here the 4 setups we investigated. We just did an angle with 5 degrees, what means the cushions moved forward. Then we have angle 0 degrees, what means the open angle is 90. Then a small recline, reducing that setup of sorry, now here it's 90 because the backrest is at 5 degrees. Here we have 95. And then finally, we make this small variation, as Bart mentioned, this ergo seat, what means we have a horizontal part below the ITs and the frontal part is somehow reclined. Okay, and so what means the seat to back support angle ranges from here from 100 degrees on the left to 90 degrees, which especially these 2 parts, especially the 3rd setup. And here we did the same analysis. We first focused on pressure mapping. And no wonder when we see here the same results, also showing millimeters of mercury from the left, from the angle 5 to the ergo seat on the right, we see especially what can be expected for the angle of 5 degrees. The frontal part of the thighs is not really loaded, what means more force is applied to the IT area. So this has the highest value. If I get a little bit more support by the frontal part, I have a reduction, further reduction, and the ergo seat is somehow in between these two because I have some setup, but the back part is horizontal, so it's a little bit increased. So not really something new and not something special we are interested here. So what we did on top, we looked then, okay, looking on the compressive strain, once again, looking on the main values, critical values from 40 to 50, 50 to 60, and 60 to 70. And this is somehow showing the same. When we look here, left side is the incline setup, highest value, horizontal lower, recline lowest, and the ergo seat is coming back. So this is somehow just visualizing that a little bit more. And then we focused on a more interesting part. It was also interesting, a little bit surprising, and we need a little bit of understanding what's going on there. We looked at first on the friction map at the surface. And when we looked on the values, like we see it, same range, same sequence as before, we see that the highest values are occurring for the inclined setup. And then we thought a little bit, okay, what could be the reason for that? The reason is we are now talking about the friction between the surface of the cushion and the patient. So let's assume I have the force coming from the back, and this force has to be somehow transduced to a horizontal force. And you can directly see, okay, if I just change my cushion angle, then the force comes here and it starts to slide. And friction is nothing else at the final state, preventing sliding. So obviously, if there we have the possibility with the inclined setup to easily slide, then it's clear that we have here the highest friction value because the cushion wants to hold you back. So this is somehow was interesting and not so surprising. But more surprising was the second part of the story. And the second part of the story is when we looked internally. And it's interesting, it's just vice versa. It's just vice versa. When we look on the shear strain values, and this is the cross section at the IT region, then we see here, just on the pictures, you see a little bit light red. And now it's getting with the angle of 0 degrees and -5, it's getting higher. And this is strange. Okay, the friction is on the left side, it's higher, and the internal stresses are lower. And the reason is, from our point of view, what we see here on this setup is when we have the inclined setup and the pelvis somehow wants to apply this force, you can directly see there is not really a counterpart. When I change that counterpart, you see directly there is some kind of the setup of the cushion blocks you. And this means the internal tissue is really getting a higher force value. So what means when I look on the friction, then there's a sliding. But when I look on the internal tissue stress, I have a higher part of the counterpart, a higher counterpart for this setup. You can directly see it. The load is going there, while he can move forward. So what means we have friction on the first side due to inclining, but internally this is somehow unloading, and we can also visualize that when we look on the VSD plot by the shear strain internally, and we can see inclined is for all critical setups, especially for the highest one, shows the lowest value. Then horizontal is a little bit higher, reclined directly. The force will be applied like this. It's the highest counterpart. And then the question is, why is the ergo seat in between? Why is the ergo seat lower than the horizontal? Because both of them in the I teaching have a horizontal part, but the ergo seat, the frontal part of the ergo seat here in this region, he takes a little bit away of this shear load. What means the frontal part, if it's reclined for the ergo seat, takes away a little bit of load, and therefore we have a lower shear strain value than for the horizontal setup. So this was for us very interesting. If we look to friction and if we look to pressure mapping, the inclined setup is not really the best. If we want to focus on internal strains, the incline seems to be the best solution. A very interesting part, and maybe also an idea that you can play a little bit to have some compromise between the two setups. And now I'm giving back to you, Bart, to come to our third case.
All right, third and final case. We have to move on a little bit, but this is a topic that is close to my heart because I've been using pelvic positioning support angles mostly in 70 degrees instead of the usual, or what a lot of people still use, a 45-degree angle. So first, a little bit about terminology. We don't talk about hip belts or a restraint anymore, and that's thanks to the great work of the Resna positioning paper on secondary positioning supports, positioning versus restraint, and a lot of the work from Michel Lang, but also the BS 8625, which appeared, the British standard, which appeared in 2019, is also depreciating that term. So important to know is that according to the British standard, the name is a description of the function based on the part of the body to which it is applied. So anterior pelvic support makes a lot of sense. A flexible PSD, flexible postural support device, is prescribed for function. That's also important to know. That's an abstract from the British standard. It is used to stabilize a part of your body, but the purpose is to increase function at other segments. So that's really important to know. You're trying to stabilize, for instance, the pelvis, and then if you're doing that, your function becomes higher at the upper extremities, or you can do more in your daily life. Next slide, please. So where do you place it? Well, anterior pelvic support shall be placed in a way to stop the pelvis from sliding. And in front of the rotation point, what it means is the pelvis rotates forwards and backwards over the trochanter or over the hip joint. So the trochanter is an easy point to palpate, and that will be the rotation point of your pelvis. So the pelvis can antiverse and the client can reach further. The client can also relieve pressures at the ITs if you are placing the secondary positioning support, the secondary pelvic positioning support in a 70-degree angle. It's also a much more dynamic way of stabilizing the pelvis, because when you are stabilizing the femurs, the pelvis cannot move forwards when the client has a sliding tendency while he stays very active. This is also a recommendation that I could find in the British 8625 standard, which was published in 2019. Next slide, please. So the clinical approach for doing this is probably that you're trying to apply a pressure. I use my hands first, where is tolerated on the client. And that's not usually a soft tissue area. So I'm always trying to avoid forces on the lower abdominal region at the groin area, because that's causing pain. It can increase tone. It can cause pressure on the bladders. And you typically would have this when you have a force under right at the ASS. And the second problem is when you go one slide further, you will see the pivotation point or the rotation point of the hip in a 45-degree angle. Example on the left, you tend to have the flexible postural support, pelvic support, right above that rotation point. So a force would result biomechanically in a posterior pelvic tilt. If you're placing the pelvic positioning support at a 70-degree angle in front of the rotation point, you should see that less, and the sliding would be less. So the clinical approach is you apply pressure with your hands first to see where it's tolerated on the client, no soft tissues, no trigger points. And then the direction of the force with your hand that's trying to block the undesired movement, that direction of the force is kind of your vector that you want to try to mimic using your pelvic positioning support. And the forearms are an extension of that direction of force. And then you look and you make an extension of that force, basically aligning your forearm with that force. And then you make a marking on the wheelchair, and that marking will be probably the best attachment point for your pelvic positioning support on the wheelchair. Next slide, please. And these are two setups. It's actually a setup that I've done 2 years ago in a nursing home in Belgium with people with the purpose of positioning, not restraining, very important. And I was using a horizontal shear force measuring tool called the iShear. And I was seeing a benefit with clients in a 70-degree angle from a horizontal shear force, total shear force measured by an iShear, which is a clinical tool, not a research tool. But you can see a difference with the horizontal shear force reduction in a more 70-degree angle picture on the right, as opposed to the picture on the left, with additional benefits that you don't apply pressure on bladder region, especially when clients are having involuntary movements or incontinent issues. That's not the smartest way to go. Am I right? Did I do this correctly? What about tissue deformation? What about pelvic rotation? And what about horizontal movements from sliding in those angles? Can we quantify this? Help, Alex.
Okay, so now we did two setups, as Bart mentioned. We did investigate on the left side, you see the angle 45 degrees, and on the right side, the angle was 70 degrees. So very similar to the two setups. And the simulation has here 3 setups. So first we apply gravity, then we apply the belt attachment, and finally we induced a horizontal movement. The goal for us was to see how stable are the two setups compared to each other if there's a horizontal movement induced there. What means we make it a little bit simple. We did not make working on muscle tones. We just applied forces here on the femur in this direction. What means in direction? And based on that, we see the risk of sliding for the setups, for the comparison of the two setups. So here, this is the first setup. What we see here is cross section as such in the sagittal plane, or in the femur region, I'm sorry. And we see here in a colorful picture the movement in the axis direction, the X direction. So on the left side 45 degrees and the right side 70 degrees. So we applied force. The belt is already it's in the right position. And then when we see here red color, this means there's a lot of movement. And when we can see, obviously, the tissue has some compliance. The femur starts to move because it's not really rigid fixed. So we see also on the right side, there's a little bit of movement, but we directly can see that when we look on the left side. the total thigh part is moving. So what means this is really showing a sliding, just getting more closer to that. If blue, this means it stays in place, it's getting red, it moves all in this direction, and what means all the tissue is moving. I will just repeat the analysis or the animation, and you will just focus on the position of the back support. Just compare that to each other. At the beginning, both are at the same location. And then you will directly see the left side. Now it starts to slide. It's moving away. The right side is still in contact. So you can directly see on that the visualization. And we also visualize that a little bit more to get it clearer. If we do only looking on the skeleton, looking only where's the position of the pelvis at the beginning and where's the position of the femur at the beginning, and just repeating here that, and focus once again mainly on the position of the pelvis. On the right side is a little bit of movement, and now you can see the left side, it really starts to sliding away. So based on that, we say, okay, this setup on the left side with the 45 degrees cannot really prevent any sliding. And when we look on the mechanical setup, it's clear somehow if the sliding is induced here, we only have the upper part of the pelvis, which is holded back, and the tissue. Here, we induce more friction. We just make a vertical compression, and we have more friction, which is preventing that you're sliding forward. The best example is if you put your hand and you push on top, you cannot really easily move it forward. And we quantified that to get it closer. First, we looked on the displacement. The black curve is showing the movement of the pelvis. So yes, we have 15 millimeters of movement, but you directly can see here there the sliding starts. At the beginning, both of them are very similar. And then for the 45 degrees pelvis setup, it starts to move a lot. And we have seen that. And what is more interesting and more critical is finally, we looked also on the rotation of the pelvis. So we have here a delta of 50 mm for the both between the both setups. And then we looked on the pelvis rotation. We see a slight rotation. And when you look on the picture, you cannot really recognize that. But when you look really on the rotation value of the mass center of the pelvis, you directly see, okay, it really rotates. And the problem is, if it's holded only on the back, on the upper part here, and it starts rotates, then you have maybe a problem. We call it automotive sector submarining. You're just going through the belt and enables you that you can slide really forward. And we here see strong difference already with 4 degrees. And if I move more forward, I have really this high risk of the setup. Finally, we looked a little bit on the friction values, which is also interesting for the sliding. We see here 45 degrees is a little bit lower. This is clear because the 70 degrees belt, to activate the friction, you have to press it down, what means you have a little bit more load. It depends a little bit on the patient. But when we start then the analysis, then we are really seeing at the end, both setups are at the same stage. There is not really a difference. But what has to be mentioned due to that movement here, we say somehow it's a wear effect. Wear means if you have a textile material and you have friction, this is not a problem. But if you're moving several times, then you have a wearing effect. And this is, in my opinion, this would be also something very critical for our skin. So I would say, although we have similar friction values, absolute values, this wearing effect is really also a negative effect. So we have a disadvantage regarding stabilization. We have a disadvantage regarding the risk of submarining, and we have a disadvantage in our opinion of the wearing effect. We are a little bit over time, 5 minutes more. We introduced here the combination of our clinical expertise and using FEA for the 3 setups, changing the seat to back support angle, changing the sagittal seat angle, and finally changing the mounting angles of a 2-point pelvic positioning. Yes, nevertheless, there are still big gaps in research on basic wheelchair setups. And so hopefully, if you have ideas and setups, we can introduce and have some further presentations at ISS. We are happy to be here. But we think FEA is not replacing. We just want to give you additional information, some ideas, what you see in reality, but give a background for it. And feel free to ask us questions in the last 6 minutes. And Bart, thank you. And thank you all for your attention.
Thanks, guys. We do have a couple questions from that were entered into the chat, and the first two have to do with the first case. And so Jillian says that her clients often confuse tilt and recline, and these clients are generally new users and often have wounds. What recline angle is shown to cause the highest level of shear and sacral pressure?
We would say directly to 20. Yeah, Bart, you would answer?
Yeah, well, I just want to say that I have the same thing, so we're confusing the tilt and recline angles. I think there's two things, repetitive movements going backwards from vertical to backwards and then from backwards to vertical. And probably you can comment on the exact values, Alex.
It's the highest
Around
value.
20, I would say.
20, 25. Yes.
20,
20
25,
is
yeah.
critical. Yeah.
And the other
20 is
part,
critical, yeah.
yeah, the other part of that question is asking if the sitting surface would change the value. And I'm
You're talking maybe
Jillian,
about the friction
yeah, Jillian,
value?
are you talking about the coefficient of friction? You can unmute.
Hi there. I was talking about just, the sitting surface, like the cushion. Like, what are you sitting on?
So you are somehow talking about the friction value. It's not included here. We left it maybe for some of the next presentations. We changed only the friction coefficient on the back support. It will change that, but the problem is if you want to prevent the shear effect and reduce the friction coefficient on the cushion surface, then you have a higher risk of sliding. So somehow give us a try for the next presentation. I will take that with us, and because we are happy to come to our ISS again.
We'll definitely have you. So another question on this case is from Kristen, and she wanted to confirm she confirmed that it seems an ergo seat is technically better in reducing overall forces than a standard seat with 5-degree angle.
5-degree reclined, what means you have this combination you have instead of that one, this combination. Based what we see here, yes. We have seen a reduction because it's a good combination. You have somehow a stopper in the frontal part for the ergo seat for movement, but still you have not the problem at the IT region, which is the counterpart reducing and inducing less shear there. I would say yes.
Kristen, did you have a follow-up to that? Nope, she says no. So the last question we had here is about case 3. And it was asked, wouldn't the 70-degree belt position limit the person's ability to lift their legs? In other words, block flexion.
Yeah, it would do that. Yeah, exactly. Because you're giving a force on the superior part of the thigh, so a flexion would impact that. Yeah. So I also see in your chat that you're working with CP folks with movement, lots of movement. Yeah, lots of movement. Okay, got it. Yeah. Well, I think you have to be creative there. Remember, you're looking at a force to neutralize a certain movement to give more function somewhere else. So if you still want to allow some degree of deflection, I can see it perhaps to limit your ability to tilt your pelvis forwards. Then I think you could go towards there's something in between a 45 and a 70. So you can probably, yeah, exactly. You said it. You can go place it perhaps closer to 50 or 55, or perhaps go in that direction. Yeah, I think so too. But of course, it's difficult to examine all these different setups. But I think it makes sense. Yeah. Thank you.
Okay, I didn't see any other questions. Did I miss anybody's question? We enabled the audio for everybody if you want to speak up and ask a question.
This is Kristen. I do have one more question if you can hear me. I'm curious about types of cushions and how they might have a negative effect on the ergo seat, such as, like an air cushion. Does that negate the ergo seat at all and take away the benefits of it?
We have not investigated it, and I have not thought about it. Obviously, cushions are behaving different.
Mhm.
And for us was also the goal not here to make differences between manufacturers. For us was the main goal here to educate and to give some general thoughts about that. But if
we
any
wanted
manufacturer is interested in that, he can really come to us and we would be happy to give him some answers. And maybe if he wants to share, we will give also the answers to you.
Yeah, I think so too, because it's almost impossible to examine all the setups, different setups, but it's more important to understand the general setup of a back support recline and the effect it has on the pelvis. So that makes more sense, but yeah.
Okay, we're cutting into people's break time now. We've run out of time. I put the CEU code in the chat. If you can't see the chat, the code is YTOAZV. YTOAZV. And so, Bart, Alex, thank you very much. Fascinating.
Thank you for
I'd
having
like
us.
to talk some more about the friction and shear at some point.
Great
Okay.
seeing you again,
Looking
Dave.
forward
Thank
to
you all for
you.
joining.
Thank you.
Thank
Enjoy
you
the
all.
rest of the conference.
Bye-bye.
Bye.
Bye, everyone.
Thank you.